But it was good because I went and just kind of looked like their kids too. Okay, it was okay. Yeah, well, the other ones are better. I love these ended though. Like, can we have a one will? It's like, yeah, that was good. Yeah, I was also kind of doing that the other instruments. Oh, no, I actually.
Okay, there's questions about the particle motion, so let me start with that. Okay, which parts do you want to?
H, I, and J.
H, okay. So H says find the particle's distance from 1 to 6. Let me start off by doing G because these are very much related here. So displacement is just final position minus initial position. We don't touch velocity. We don't divide by time. So it's just final position minus initial. Okay, so for those of you online, this is the handout that I gave out on Friday, and I didn't give it to the second period. I forgot to, but I sent it out the link and I put it in the chat link as well. Okay, final position minus initial position. So we need to find the position at 6 minutes, and then find the position at 1 minute. Okay, so this is calculator set up here. So we can plug 1 into our position function, plug 6 into the position function, find out where the particle is located at these moments in time. So x of 6 is 37. So that means 6 minutes in, this particle is located 37 meters on the x-axis, and then x of 1 is negative 1.75. Okay, 1 minute in, particle is located at negative 1.75 on the x-axis. So final position minus initial position, we want to figure out between 1 and 6 minutes, how far has the object traveled and in which direction? So 37 minus negative 1.75. And this gives us 38.75. Okay. That means between 1 and 6 minutes, this object is going to end up 38.75 meters to the right of where he started. So he's going to start at 1.75. 5 minutes later, he's going to end up 37. So he's going to end up 38 units to the right. So the connection between displacement and distance is that we're also going to use our final and initial positions, just like how we did with displacement. So to find total distance, we still need x of 1. We still need x of 6. But we may need another time value, depending if this object changes direction somewhere between 1 and 6 minutes. And if we look up at part B, where we did our velocity sign line. Object's moving left, then right, then left, then right. So 4 minutes in, it does change direction here. And 4 is between 1 and 6. So we also need to include his location 4 minutes into his movement.
Is it be like a velocity graph then?
It is.
So you just use that anyways?
We have to use velocity graph because otherwise we wouldn't know when he changes direction.
Okay.
Yeah.
Why did you include the negative value for B?
We did include it because they specified it's for all real numbers. So we always have to look at the restriction to see if it starts at 0 or if it includes negative numbers as well.
Okay, so for the last one, it was because T was greater than 2.
Exactly,
Okay.
right. Yeah, so the restriction is always going to tell you, or the initial problem will always tell you what to do with the number line.
Okay.
Yeah, I just said that we don't use velocity, but we kind of do for distance just to find the location of a change in direction.
Okay, so just zero.
Close. It needs to be velocity 0, and there has to be a change in signs.
Okay.
Right.
Okay, yeah, and it has to all be
And
in
then
the interval.
Yes, has to be. You're right. Good. Yeah, it has to be between 1 and 6. It's got to be a location where the particle stops, and it's got to be a particle position location where the particle changes direction. Change direction, we can tell by looking if there's a change in sign. Yes, yeah. So for part B, when it says when does particle change direction, we have to set velocity, find velocity, set velocity go to 0, populate your velocity sign line, and then from here, then you can read it off your graph, right? All right, so x of 4, we have to find the location of this object at 4 minutes, and 4 minutes in, plug this into your calculator. It ends up at negative 31. So to find the total distance, imagine you're just walking from this location to this location to this location. And you're just walking, you're just counting your steps. So every step you take, you're just moving the next integer over. So maybe you don't have to do this, but maybe if it helps to visualize yourself walking along this number line. Let's say this is negative 1.75. And then you walk all the way over to negative 31 on the number line. And then you're going to go all the way over to the right to 37. So you're starting here at negative 1.75. You're walking to the left, and you're counting your steps. And then once you reach negative 31, you're going to stop, turn around, and you're going to move to the right. And you're going to count your steps to see how many steps it will take to get to 37. So from negative 1.75 to negative 31, how many steps would you have taken to get from this location to this location? Yeah, so you can just basically subtract these numbers and then just make sure that you convert any negatives to positive, because if you are counting steps, you're always counting positive steps, right? You don't count negative steps. So 29.25. And then you turn around from negative 31 and you're walking from negative 31 all the way to 37. So you got to go from negative 31 to 0 and then from 0 to 37. And counting those steps, you should get 68. So you took 29.25 steps to the left, and then you took 68 steps to the right. How many steps have you taken in total? You just add those numbers together. All right, does that make sense?
For acceleration, is the unit, like, for example, meters per second squared? Like,
That's
why
right.
is the seconds squared?
Because, right, the reason because velocity is, let's say, is meters per second, right? And but now acceleration is the rate of change of velocity. So it's the time unit, or it's the unit for velocity over seconds. right? So change in velocity over the change in time. So meters per second divided by seconds is same thing as meters per second times 1 over s, which is meters per second squared. But if you leave it as meters per second, that's fine as well. But a lot of people would just reduce it to meters per second squared for acceleration. Okay. Next up, at t equals 2, is the speed increasing or decreasing? So increasing, decreasing speed, we have to compare signs. So we have to find the velocity at 2. We have to find the acceleration at 2 and see what the signs are indicating to us. Excuse me. So velocity at 2 is -12. Acceleration at 2 is -4. So they're both same signs, which indicates that this object is speeding up. So speed is increasing since velocity and acceleration have the same signs at t equals 2. Mm-hmm.
So you don't need to find the velocity for J, just if the acceleration is positive, the
Right.
velocity is always increasing. Is that
Exactly.
okay?
Yeah. And the reason why is because the reason why this is not talking about velocity is because it's asking about whether velocity is increasing or decreasing. So it wants to know, is the velocity graph looking like this, or is it looking like this, right? Is it rising or is it falling? So if I'm talking about whether a velocity graph is rising or falling, I'm really talking about the slope of velocity. So if I'm talking about the slope of velocity, then that's referring to the rate of change of velocity, which is really talking about acceleration. So since acceleration is a positive 41, that's indicating to me that the slope of velocity is rising, is positive. So therefore, my velocity is increasing.
Okay, so it doesn't matter, like even if the velocity graph is like about to reach 0, so it wouldn't matter because it's still like increasing, right?
It's still, yeah.
If there was like a negative velocity.
Oh, if it's negative velocity, yeah. If it's any part, if velocity is going down, then that is still considered a decreasing velocity slope, right? Yeah.
For number 12 on page 8, I was just like wondering, so I got a different answer because maybe I found like the side lines first and then used Pythagorean theorem instead of like using it with knots per hour.
Mm-hmm.
Are we just like able to use Pythagorean theorem like find like C right? Or like the
Hypotenuse, Z.
yeah, like the rate of change of that if we have the rate of change of the other two?
Yes. Yes.
I don't know, I just don't know.
Let me find that. Okay. All right. I can work that out. Page 8. Is this on the?
Yeah.
Oh, okay. Okay. See it. Okay, the 2 boats leaving. So this is okay, one's traveling north, the other's traveling west. So this is the only way we can draw it, right? Y is rise to the going up, x is going to the left. Both dx dt and dy dt are positive, 12 and 15. Right? A squared plus b squared equals c squared. We go through Pythagorean theorem, and we can find dx dt and dy dt. I'm sorry, we can find x and y because we know how fast he's going and for how long. So 12 knots per hour versus 15 knots per hour over a 2-hour period, it's going to be 24 knots and 30 knots. So that's going to be my x and y. And then Pythagorean theorem is based off of the 24 and 30, which is a squared plus b squared equals c squared. I get 38.419. Is that what you got?
I think that's why I did it wrong.
I see.
Okay, yeah, that makes sense, so.
Okay.
And then for number 2 on page 17, I was just like wondering if for a cone, if it says the tank is half full, then we use the volume, right? Like half the volume or half.
Yeah, half full is talking about half the height. Yeah. Let me see. Yeah, I think that's the way that we talk about like a glass being half full. It doesn't really matter what the radius is. We just look at the.
Okay.
Yeah.
So when the value can change throughout the problem, you don't put the numbers until after you do the derivative.
That's right. Yeah, you have to hold on to that variable up until you find the derivative, right? Because if a value is changing over time and you don't hold on to that variable, then you're saying that that value is never changing throughout the whole problem. That messes up with the calculations.
Page 6 of the review, how did you get y is equal to 8?
Are you talking about the number 6 and number 7?
6a.
6A, okay. Let's see. Okay. What's your question again?
I mean, how did you get z is equal to 10?
Z is equal to 10. Okay. Okay, so
Wait, sorry. X is equal to 8. How'd you get x?
when 10 feet of rope are out. So when 10 feet of rope are out, that means the hypotenuse is at a moment in time is 10 feet. And since my y component is 6, I can use Pythagorean theorem and say a squared plus b squared equals c squared and just solve for my x squared or my a squared.
Okay, I did my math. You could also use 3, 4, 5.
Yeah, it's also right. It's a 3, 4, 5. Variation of a 3, 4, 5 triangle.
Could you do number 5 on page 14?
Okay. Page 14. All right, at noon, ship A is 100 kilometers west of ship B. A is sailing south and B is sailing north. How fast is the distance between the ships changing at 4 p.m.? Ship A is traveling at a faster rate than B. What we want to do is this is not the diagram that we really want, because we want to try to fit this into a right triangle so we actually find all the relationships a little bit better. So we're going to pretend like as if B is standing still, and then we just want A to move, and then we'll just let A absorb the movements of both A and B. So traveling at 35 kilometers and 25. So that means, after 1 hour, they're going to be x plus y squared. Yeah, they're going to be 60 kilometers apart from each other, right? Because if one is moving away from the center, 35, another one's moving away from the center, 25, an hour later, they're going to be 60. So the idea is that after each hour, they're going to keep getting 60 kilometers away from each other. So it's like as if one is moving at 60 kilometers per hour, and then in each hour that passes, vertically, they're separated by another 60 kilometers. So we can think of it this way, where we have x is constant, y is moving, and then z is also moving. So we say x squared plus y squared equals z squared. Hey, ship A is 100 kilometers west of ship B. So that is the initial 100 kilometers here. How fast is the distance changing between the ships at 4 p.m.? So we want to figure out dz dt. That's the unknown. Y is, well, if we know that their distance is changing at 60 kilometers per hour, then after 4 hours, Y is going to be 240 kilometers away from his starting point. So Y is going to be 240. And to find Z, we can use Pythagorean theorem. A squared plus B squared equals C squared. And that's going to get us to 260. dx dt, we know that this horizontal distance between them is never going to change. So dx dt is 0. And then now we have 5 out of the 6 variables accounted for. I can solve for dz dt by just plugging back into my derivative equation. Okay, multiply that out. We divide by 520, and we can solve for dz dt. Units is kilometers per hour.
Does it matter which side you label X and Y? No.
That's it. As long as, yeah, as long as you're consistent within your variables within your problem.
Example 3 on page 13 of the packet. This is
Example 3. Okay.
I don't know how to approach it.
Okay, so this is in our notes packet here. A spherical balloon is being inflated at a rate of 10 cubic centimeters per second. Find the rate of change of the surface area of the balloon at the moment when the surface area is 64 pi. So if I gave this problem to you, I'll give you the formulas here, volume and surface area. We know we have to involve the derivatives, so I went ahead and I found each of the derivatives. This ends up my derivative for r cubed is 3r squared. So v becomes dv dt, r becomes dr dt. Clean all that up, and we get dv dt equals 4 pi r squared dr dt. Next up, surface area is 4 pi r squared. We find the derivative, that becomes 8 pi r dr dt. That's my ds dt. So balloon is being inflated at a rate of 10 cubic centimeters per second. That's my dv dt. That's 10 cubic centimeters per second. Positive. Find the rate of change of the surface area. So I'm looking for ds dt. At the moment, when the surface area is 64 pi, so s is 64 pi. Okay. Good with that. With that information that we've gathered. Okay. So we're looking for ds dt. So if we're looking for ds dt, it'll be nice if we just had r and dr dt, because then we can just plug in and find our answer. But we don't have those data, right?
So could you use 64?
There you go. Yeah, so 64 pi, we have this, so 64 pi can plug in for s and solve for r, and then if we solve for r, then that's one piece of the puzzle. The other piece of the puzzle is we don't have dr dt, but maybe this 10 can help. How do you think this dv dt value could help?
Well, if you plug it back in.
Into this equation, right? So I can plug 10 into here, and then whatever r value I found, plug it in here, and then now that gives me the enough information to solve for dr dt. If I have dr dt, then that's the second piece of the puzzle that I need. Once I have r and dr dt, I can just multiply that out to get the ds dt. So this is what the end result looks like. If I plug 64 pi in for s, I get 64 pi equals 4 pi r squared, divide by 4 pi. R squared is 16, r is 4, so there's the radius that I need. dv dt was 10. Plug 10 into my dv dt equation, replace r with 4, and then I do 10 divided by 64 pi. That gets me my dr dt. That's the second piece of the puzzle. So now that I have r equals 4 and dr dt equals 10 over 64 pi, which I reduced to be 5 over 32 pi, then even though the problem gave me indirect pieces of information, I was able to use the formulas available to help me get to the variables that I really need, which is radius and dr dt. Once I have radius and dr dt, then I can just insert them into my ds dt equation and solve for ds dt.
You just kind of use like all of it at the same time.
Yeah, it's like a puzzle. It's like, okay, this is what I need to get to, but this is not the data that I have. So what can I do to eventually get to where I need to go?
For a theta problem, will theta always be across from the?
The diagram will be drawn for you, so
Okay.
there's no guessing work. You'll know exactly where theta is.
Okay, so it won't necessarily always be tangent, or specifically always one trig function you start with.
Yeah, it may not always be tangent That's right. Yeah.
It just depends on what you're given.
Yeah. It depends on what you're given. Yeah.
Okay.
So whatever two sides information you're given, then you want to use those two sides.
Mhm.
Okay. What else do you guys want to go over?
Also, number 2 on page 16. Also, experience building.
This one here.
For number 2.
Oh, right. So, it says, suppose this is a little bit different, but this is also good too. Suppose that a spherical balloon grows in such a way that V is equal to 4 root T inches per second. Sorry, just cubic inches. How fast is the radius changing after 64 seconds? So V is equal to 4 root T, which is 4 T to the 1/2. Now I have two V equations here. You see that there's a V equals 4T to the 1/2, and there's also V is equal to 4/3 power cubed. This connects the relationship between volume and radius. This is what we're used to. This is a little bit different because it's just indicating the relationship between velocity and time. So I'm going to gather some information here. I know that after 64 seconds, I can figure out the volume at that moment in time. So I'm just going to just gather information here. So V of 64 is just 4 times 64 to the 1/2. And square root of 64 is 8. 4 times 8 is 32. I can also find dV/dt, but this is a little bit different because this already has the independent variable t. So V becomes dV/dt, which is fine. But here, if I find the derivative, I get 4 times 1/2, which is 2t to the negative 1/2 times dt. And we know that if I'm finding the derivative with respect to itself, it's just going to wash out, right? We basically have the independent variable here, so there's no need for dt. So we know that dV/dt can be represented as 2 over root t. So we know that the rate of change of the volume at 64 seconds is 2 over root 64, which is 2 over 8, which is 1/4. So the problem is a little bit more involved because before they would give you dV/dt, but here you got to actually find dV/dt value normally this would be a starting point, but now we have to do a little more work to get there. Now it should feel more familiar. Yeah, so now let's do that. 4/3 power cubed becomes 4/3 pi times 3r squared dr dt. Three's cancel out, 4 pi r squared dr dt. Okay, how fast is the radius changing? We're looking for dr dt after 64 seconds. So 64 seconds in, we already found dv/dt, so we know this is the moment in time that we're referring to. We still need to find the radius. So to find the radius, we have to plug into our volume equation. Well, we know that V is equal to 4 root T, so we know that the volume at 64 seconds is 32, so we can use that information to help us find our radius. Okay, so 32 divided by 4/3 pi, the same thing as 32 times 3 pi over, I'm sorry, 3 over 4 pi. And that ends up giving us 24 over pi. 24, yeah. Okay, the cube root of that, so r is equal to the cube root of 24 over pi. So now we have everything that we need. We have r, which is cube root of 24 over pi. We have dr/dt, we have dv/dt, which is 1/4, and then we can now work backwards and solve for dr/dt. It's just a messy number crunching calculation in your calculator. You take this number, find that decimal, divide that over to the other side, and get dr/dt by itself.
So is the only reason you found 32 at the very beginning, so you can use it to find the RT? Wait,
I found this 32 at the beginning so that I can actually find the radius, which is needed in my dv/dt formula.
When would comparative growth rates be negative?
Comparative growth rates.
When X is approaching negativity, would
Yeah, we don't do comparative growth rates if it's negative infinity. You can only do it if it's positive infinity.
okay, so then what would you do?
Yeah, if I can use comparative growth rates, then I'm kind of forced into seeing if L'Hopital's rule can work.
So just, there won't be like any.
Yeah.
So when you're doing the limit, for L'Hopital's rule, and its x goes to infinity, you don't have to put it in the derivative form to use the L is less than or R is less than P is less than E.
You don't have to, right?
Just like directly look.
You can go directly into it, yeah. Yes.
Could you find particles distance for particle motion problem?
Yeah. So this was page 41 that you picked up at the end of class. Do you have this worksheet here? Okay. So to find total distance, you're going to find your locations at 1 and 6, just like how we did with displacement. But we may need additional location between 1 and 6 if there's a change in direction. So if we want to figure out there's change in direction, we have to go to our velocity sign line. We did that for part B, looking to see, okay, where is the velocity 0? If there's a change in direction, there happens to be a change in direction at 4 minutes because there's a minus followed by a plus. So we also need to find the location of the particle at 4 minutes. Plug that in the calculator, we get negative 31. And then we're just imagining ourselves walking from this location to this location, back to this location, and we're just counting our steps. And at the end of our trip, we just total up the number of steps we've taken. So from negative 1.75 to negative 31, if we subtract those numbers, it ends up giving us 29.25. And if in your calculator, if you're ever subtracting numbers and you get a negative number, just convert it to a positive number because you're just counting steps. And then from negative 31 to 37, if we add up, if we count our steps from here to here, that's a total of 68 steps. Add those two together, that's our total distance.
I do remember 7 on page 32 of the packet. It's on the AP office.
Which page?
32.
Okay, which one is this?
Number 7.
7. Yeah, 7 is a strange one. I'm still trying to figure out how to fully, yeah, let's not worry about that one. Yeah.
Did you also try to for C for number 7 on page 35? Yeah.
Bye. Let's see.
We have a problem like this where it's like where it passes the week and where it overflows and all that.
No, this is more of an AP type problem, but let me see here. Okay. 10 meters from the bottom of the tank, there's a hole in the tank. It's from find the rate at which the water is rising in the tank until it reaches the leak. P sub 1 is 10 times 4 pi. Let's see. There's 20 meters in height. Okay. 4 meters radius, constant rate of 5 cubic meters per hour. Meters from the bottom of the tank, there's a hole in the tank. The part C, let's see, T sub 1 is the time it takes to get to that first 10 meters of the tank. And it's 1 over 4 pi because because that's my DHDT. That's the rate at which my height is increasing.
So that's the day of home burning. We saw that on this 1340. We have a few new who did not come in yet, so we need to pick up the envelope. Thank you.
So 1 over 4 pi, we want to figure out, it's rising at this rate. How long will it take before it reaches the height of 10 meters? We're working backwards and we find T sub 1 is 125 hours. And then next up, we want to figure out until it reaches the leak, 5/16 from T2, where it will reach 10 meters. So basically find the 2 times, 1 time to fill up the first 10 meters. But then after the leak, it's rising at a different rate. And if we subtract these 2, we can figure out the time it'll take for the tank to overflow. Yeah, that's a little much. Yeah. Okay. That good? Mm-hmm.